This is Lab 2, Charge Tapes, Part 2. In this lab, we will demonstrate the charge tapes exerting an electric force on each other and experience a gravitational force, and use this model to estimate the number of charge on each tape necessary to float one tape above the other. This lab also explores polarization of charges, as well as how charges affect the object's behavior using Newton's second law and electric field and force. This lab is a continuation of Lab 1, however, this lab models the charge tapes as lines of charge rather than point charges. Some key concepts that will be necessary for understanding the physics behind this phenomenon is Coulomb's law, which states that the electrical force between two charged objects is directly proportional to the product of the quantity of the charge on the objects and inversely proportional to the square of the separation distance between the two objects. Similarly, the gravitational force is equal to the mass of the tape times the acceleration due to gravity in the negative y direction. To find the charge on one tape, we will use Newton's second law. On the floating tape, there's no external forces as the tape isn't moving. Therefore, the magnitude of the electric force by the bottom tape equals the gravitational force of the upper tape. For the floating tape, the procedure is to suspend one of the U-tapes from an object, such as a desk, and then hold a second U-tape above the first until it begins to float. And we record the distance between the U-tapes until the top floats. The measurements we will need to do the calculations include the distance between the two tapes, 0.0198 meters, the length of the tape, which is 0.2 meters, the tape width, which is 0.232 meters, and the surface area of the tape, which is 0.2 meters times 0.232 meters, which is 0.00464 meters squared. Here we have the calculation for the problems. As mentioned above, we use Newton's second law to find the magnitude of the electric force, which is equal to the magnitude of the gravitational force, which is negative 0.000196 newtons. Rearranging Coulomb's equation and solving for charge gives us Q is equal to 9.24 times 10 to the negative 9th coulombs. For our model in glow script on the next slide, there are some assumptions that we need to take into account. Both pieces of tape have equal magnitude of charge. The charge is distributed evenly across the surface of the tapes. We ignore air resistance, and we model the tapes as length rather than point charges. We can also model this phenomenon in glow script. The initial code lists the constants as well as the observed values. Using these values, we estimate the charge on one tape. Next, we have a constant function to reference that will calculate the electric field. The next function creates a line of charge, as well as creating objects to represent the two tapes, with each tape model as a collection of point charges placed side by side in a line. The y components represent the location of the charge, as well as the n, which represents the number of tiny charges on the tape to calculate the electric field width. Next, we calculate the electric field and force. Each tape is simulated as a line of point charges, DQs. The top tape in the system and the bottom tape is part of the surroundings. At the location of each DQ on the top tape, there's an electric field produced by a collection of charges that make up the bottom tape. We will create n arrows for these electric field vectors, placing their tails at each DQ on the top tape. We will calculate the electric force on the top tape due to the bottom tape by adding up the forces from each DQ in the bottom tape as they interact with each DQ in the top tape. We ignore the interactions between the DQs within each separate tape. Here we have our output. The red arrows represent the electric force due to the charges on the bottom tape. The white arrow represents the net force due to these small charges, while the green and yellow arrows represent the individual gravitational force and net gravitational force. The charge from Lab 1 is negative 9.2 times 10 to the 9 coulombs, which you saw before. The magnitude of electric force due to the previous charge was 3.4 times 10 to the negative 4 newtons. The magnitude of gravitational force was 1.96 times 10 to the negative 3 newtons, which also was shown above. The new electric field has 17 times the magnitude from before, and the tape charge with the distributed charge is negative 5.26 times 10 to the negative 8th coulombs. Now, what if we model each of the tapes as a single point charge like the previous lab? So in the point charge model, the charge would be negative 9.24 times 10 to the negative 9th coulombs, but in the line charge model, it's negative 5.24 times 10 to the negative 8 coulombs, which is 5 times more. Why do these estimates differ, and which value is more likely to be closer to the real value? When using a line charge model, each piece on the top tape experiences a force from the bottom tape. We expect Fe to be much less because using the charge determined in the previous law, the charges are distributed further apart, so a greater charge is needed to cause the same repulsion. The line charge is more accurate as it reflects a real-world principle that charge is distributed rather than concentrated at one point.